Press that. All right. Okay, so yeah. Well, hi everyone. Thank you again for dialing in. I'm just repeating myself since I just started recording. Um, so I'm just going to go down the list to see who we have online. So we have, let's see, myself, Shuai, one of our presenters today, um, Ariel Deutsch, Carly Peters, Daru Han, James Head, Jamie Zalay, Jeff Plesha, Kristen Luxinger, Mahesh Anand, Marcella Roth, Margaret Landis, Philip Phipps, Rosemary Killen, Junichi Hariyama. So we have a nice international crowd today. So yeah, thanks everyone for dialing in. Did I leave anyone out? Okay, so I did have two things on the agenda for today. I think I saw Ariel Moulet from the Sophia team dial in, but it looks like she may have dropped off. So maybe we'll leave a few minutes for that at the end. But Ariel had a quick announcement she wanted to make about some of the Sophia lunar observations, but she said that shouldn't take more than a few minutes. So we'll see if she's able to rejoin. But otherwise, our presenter today is Shuai Li, who is joining us bright and early from Hawaii. And Shuai agreed to talk to us today about some of the recent work that he and his co-authors published on the detection of hematite at high latitudes on the moon. So Shuai, whenever you're ready, you should have access to share your screen if you have slides.
Okay. Can you see it?
Yeah, that looks great. So yeah, so we're seeing there we go. Yeah, that's perfect. And so I will, before I turn it over to Shuai, just a reminder to everyone, if you are not speaking, please have yourself on mute, and feel free to have your webcam on or off. That's up to you. And so, Shuai, do you want us to wait until the end for questions, or should we interrupt you in between if we have questions?
Can just interrupt me, no worries.
All right, sounds
Yeah.
good. Okay, so over to you whenever you're ready, and thanks for making the time today.
Okay, thank you, Percy. Thank you for having me here. It's so glad to talk about my recent work about a hematite on the moon. As you can see, this is a screenshot of the title of the paper, and I want to thank all my co-authors for their contribution to this work. Okay, let's start. Wait a second. Oh, yeah. Some introduction. As we know, the water rock reactions on the moon, on Earth, Mars, and even asteroids are quite common. And one of the common products is hematite. As we can see on Mars, it's widespread on the surface, looks reddish. It turns out that in recent days, it's a very good time to look at it into like the sky, to look at the Mars. This looks like orange in Hawaii. I'm not sure, like East Coast. Yeah. So, well, like the whole project at the very beginning, actually, I was not clear whether, I can see hematite or something else. I mean, if you are interested in the whole survey, I can tell afterward. Anyway, so as we know, it's very common as a alteration product, hematite present on a lot of body, like planetary bodies. And on the moon, it's quite different because we know the solar wind can bombard the surface continuously, and after the formation of the moon. And I always know the majority of species of the solar wind is hydrogen. So it makes the lunar surface highly reduced. And this is also consistent with what we see in Apollo samples, tons of metallic iron. However, until like recent decades, a major discovery about the moon is water and water ice on the moon. And this inspires me to think about the possible water rock reaction on the moon too, even though the water is very low. So here's the water map I made, and this is the polar projection. The left side is North Pole, the right side is South Pole. Sorry, I didn't put the latitude. This is from 75 to 90 degree, the same as the red plot. This is for water ice we found in the lunar permanent shaded regions as shown as dots. So you can see there are water, even though only a few hundred ppm, but there's also water ice, like can be few tenths weight percent. And if there's water on the surface in a polar region and the rock there, right? So it's a very intuitive to think about that possible any reactions on the surface, whether we can see it. And also their theoretical studies also support the aqueous alteration and the lunar condition as shown in these papers. But as I mentioned in the first slide, so the surfaces and both surface and interior are highly reducing. Even though you can form some alteration products, it may reduce by solar wind like very fast. And this is supported by the the iron 2 plus and also iron metal in Apollo samples we see. And even though there's some like studies showing ferric iron in Apollo samples, but it has a long debate whether that's formed on the surface or it's due to terrestrial contamination. So this is still a big unknown. Hopefully we can have we can answer this question by the sealed samples or in future sample returns. And also there is another interesting study also inspires me. It's a detection of a possible iron 3 plus by the Galileo solid state imager. I show a figure here. This is the SSI spectra. And as pointed by the red arrow, you can see some of the spectra shows a weak kink at around a 0.66H bands. You can see here. Normally it will like the first one, but some of them showing the weak absorption. At that time, I think limited by the information. There are multiple interpretations. First, they thought there could be some ferric iron in clinopyroxene, or it could be due to the presence of phthalosilicates, or it could be ilmenite. So with more data and also hyperspectral data, we should be able to resolve this problem. And so that's why we use, that's the data we use, the moon mineralogy mapper data, the global reflectance data. We use it to search for hematite on the moon. The reason, yeah, as I said, it's a long story why we choose hematite. One of the major reasons is it's a spectrally distinctive. It's very spectrally distinctive. So as shown in this figure here, this is from 500 to 1200 nanometer wavelength range. This is reflection data. And I plot all the major minerals or other species on the lunar surface in compared to hematite as the red one. So the hematite spectrum has two distinctive absorption features. First one is very strong, near 850 nanometer. The second one is near 660 nanometer. This is essentially what we see in the SSI, the Galileo solid state imager show, the weak feature. So there is a strong one actually. So I mean, they don't have the coverage, but MQ data does. So we can use the two features to search for the presence of hematite on the surface. The detection is quite simple as shown here. So there we do see the very interesting features in the MQ data, similar to hematite as shown the left plot, pointed by the two red arrows. You can see there's absorption near 850 nanometer and also a weak absorption near 660 nanometer. And the black line is the pure hematite spectrum measured in lab. in the USCS laboratory. And on the red plot showing the three spectra after continuum removal, you can see the major absorption features match very well with the lab data, the pure hematite spectra. So you can see the center and also the bandwidth. The bandwidth of the hematite spectra we see on the moon also match with the terrestrial hematite spectrum measured in laboratory, both of the features. So it's strongly indicated this is a hematite, not anything else. And also I will touch a little bit more in following slides. We tried to do some spectrum mixing. And if there's no hematite, you cannot reproduce the absorption feature. And actually, the reason, I can talk a little bit, the reason I think I choose hematite as a target at the beginning is because when I looked at M-cube spectra, I noticed this band shift first. So as we know, as a lunar spectroscopist, I think everyone should know, like the pyroxene absorption, the minimum absorption is around like 900 nanometer. So this one is definitely way shorter than 900 nanometer. This is abnormal. And actually I spent like a few months to realize what the species are, and then came out this work. Yeah, so this is the map, global map. This is first optical detection of hematite. This is the North Pole. This is South Pole. This is the band depth, the integrated band depth near 850 nanometer. The yellowish color means the band depth, integrated band depth, IBD is around 0.1, while the reddish is 0.7. So the redder, the stronger absorption means more hematite. After we see this feature, we want to know whether some like distribution trend so we also did a global search, and we found out that it only appears at a latitude above 60 degree in both hemispheres. But here I only show the distribution from 75 to the polar region. And also we noticed that it is mostly associated with the east and the equator facing sides of the tropical highs. Not sure you can see these craters. You can see the crater wall. It's only on the west side of the crater wall, means like facing east. And also it's exposed more on the near side. So this zero that's facing us, zero longitude, you can see this is North Pole. You can see it's more on the near side. This is 180, that's the far side, you don't see much. It's more obvious on the South Pole. So you can see this is near side, zero longitude. You can see way more hematite exposures than the far side. Yeah. So after we see this trend, we're curious whether there's some like detection bias. So we plot the we plotted the detection with albedo. So this is M-cube reflectance at like a 1.5-ish micron, and this is absorption strength at the 850 nanometer. This is the indicator for the hematite presence. So this is a northern polar region, southern polar region. You can see there is no obvious correlation with the albedo and also the hematite abundance. And this is south polar region. And also we plot the lower surface slope because we're curious whether this is only like associated with some degree of slope. And it turns out there's also no clear correlation. So you can see this is surface slope, this is the abundance of hematite, and this is the northern polar region and a southern polar region. So there's no albedo dependence, there's no like surface slope dependence. And also we test the viewing geometry. So this is M-cube phase angle at the detection pixels. And also this is the absorption strength of hematite. You may see some very weak correlation. We interpret this weak correlation to as due to the higher abundance approaching to the close to the pole. So that means like a higher latitude, you would expect to see a slightly higher hematite. Uh, as we all know, when it goes to higher latitude, the viewing geometry is big, the phase angle is bigger and bigger. To further illustrate these effects, we plot a histogram. So the histogram can explain. This is the phase angle of all examined pixels versus the hematite bearing pixels. You can see there's no clear offset. So it's like the mean, the average, and our standard deviation. It's consistent with the examiner data. So it's not biased towards either high phase angle or low phase angle. So there is no any a clear viewing geometry dependence. And also, fortunately, MCube has multiple observations on the surface, and we examined one case at a Rodesvinsky crater. So you can see there are repeatable detections of hematites. The blue curve, this is from OP2A, while the red curve is from OP2C. So this is a 2x2 pixel average, and also compared with the USGS pure hematite spectra, you can see the features still present and also match with the lab data. And the band center and the band width match well with the lab data. Yeah, so this is we are quite confident after like thorough examinations. We are quite confident about the presence of hematite on the surface, and then we propose a model to explain the formation mechanism for it. The first obvious distribution pattern is the dichotomous distribution on the near and far side of the moon, if you recall. So there are more hematite exposures on near side than the far side is more obvious on the south polar region. We think this is due to the effects of Earth magnetotail. The Earth magnetotail plays two roles. First, it reduces the solar wind hydrogen by over like even 99% hydrogen. So when the moon in the magnetotail, it is more oxidizing because there's way less hydrogen. But at the meantime, solar wind blow oxygen from Earth atmosphere into its magnetotail. So in the magnetotail, the oxygen it's quite dense, so it can be delivered to the surface. So the whole magnetotail environment make the moon way more oxidizing than the moon is outside of the magnetotail by reducing the hydrogen, but at the meantime provide oxygen. So we think this is the mechanism for the most hematite formed on the near side. So that explains why you have way more hematite on your side. And also we did some rough calculation based on the oxygen flux delivered from the Earth to the moon. This is observed by Kaguya mission. I used the value provided in Terada et al. 2017 paper. And it turns out the oxygen impasse in like around 100 million years is sufficient to oxidize around 10% hematite. I'm not using like a 2 billion years or even longer or 1 billion years. I'm using like 100 million years because this is a kind of like a average exposure time people found in Apollo samples. So 100 million years is enough to oxidize like a 10% hematite. Oh, here I forgot to explain. This is the Artemis observation of solar wind. This is a lunar phase. So you can see that from like a 330 to 30 lunar phase, this is in the magnetotail. You can see the red, the yellowish, the flux is run like a 10 to the 5th, while the purplish is like 10 to the 8th. So when the moon in the magnetotail, the solar wind flux drops like to even less than 1% of that out of the magnetotail. And also we see a strong latitudinal dependence as explained. So this is a histogram. This is from global map. So the red bar is the hematite exposure. We don't see many exposures less than 60 degree, almost nothing. But as goes to around like a 70, 75, you can see more and more exposure as approaching the pole. And at first I thought, because the at the beginning of the project, I'm thinking about a water rock reaction. So I'm thinking water, the role of water all the time. And when I see this trend, I feel like, this must be associated with the water abundance. Yeah, you can see this is the blue line is the average water content we mapped, and the gray region is the standard deviation. You can see there is like a huge increase above like 60 degree to the polar region, particularly in the South Pole. You can see like exponential increase in water content. So we think the water also plays a role in the formation of hematite, and also the solar wind flux is also low in the polar region. So here the dashed line, this is a solar wind flux normalized at a 0 latitude. This is like a multiplied by 1,000 to match the figure. This is just a cosine of the latitude angle. This is like a very rough approximation. But you can see as you go approach the pole, because the shape of them, the moon, the body. So the polar region, the solar wind flux is also very low. So it means like in the polar region, it's also relatively more oxidizing, and also it's more desirable for the formation of hematite. That's also may explain why we see more hematite in the polar region, while like near the equator, because the solar wind flux is so strong, even though you may be able to form some hematite when the moon in the magnetic tail, but when the moon is out of the magnetic tail, it can be reduced maybe very fast by solar wind hydrogen. And also, there is another major feature about the distribution is about the east side, the east facing and equator facing side of the tropical highs. This is showing way more exposure than the west facing or pole facing. We think this is related to the interplanetary dust. Because there's a asymmetric distribution of the impact. This is as shown in Herning et al. 2015 paper. There were a lot of there was high flux impact in the down terminator than the dust terminator, and also the when the flux change, the environment of oxygen and also solar wind also changed. So we compiled all the factors together to do some simulation. So again, the left side is the distribution. So this is I binned the exposure and normalize it with the longitude. So this is negative 180. This is a far side, and a 0 longitude. This is a near side, and also binned with their azimuth angle. So PF pole facing, polar facing, east, EF east facing. So you can see this is a near side has more exposure, and also the east equator facing side has more exposure. This is figure A is northern polar region, figure B is south pole. You can see the southern polar region is more obvious, so you can see more at east facing side and also the near side. So as I said, I put all the factors together, did a very rough simulation. The interplanetary dust impact, like Earth's oxygen when the moon in the magnetic tail. I put everything together and do a simulation. You can see on the near side, the environment is more suitable for hematite formation at the east and the equator facing side. Particularly, you can see here. But on the far side, there's no obvious difference, because you can receive the impact almost identically, whatever east or west facing side, but there's no oxygen. So that makes the reason why there's no obvious like east or west facing side. The topographic has more or less hematite, but it has a dynamic distribution on the near side. It's very rough, like a simulation, but it can explain why we see more on the east or equator facing side topographic highs. As I mentioned a little bit earlier, we also tried quantitative modeling work to explain to understand the abundance of hematite, and also try to see whether we can fit the spectrum without hematite as a member. So this is the blue line. This is the measured MQ spectrum at Rodesvinsky crater, and we try to without hematite as shown in the red line. So there is no hematite. We try to use all the major enantiomers like agglutinates, volcanic glasses, pyroxene, clinopyroxene, autopyroxene, plagioclase, olivine, and ilmenite. You can see without the presence of hematite, you cannot make the absorption center shift towards to like around 850 or 870 nanometer. So the shortest, maybe you go to like a 900. So if you look at Rachel Klim's synthetic pyroxene work, what she showed is the minimum absorption or like a source of a pyroxene at near 1 micron is the shorter wavelength is around 900 nanometer. Well, like after we include hematite as an member, the black lines, you can see we can fit the spectrum very well with the measurements, and also we can get the abundance. We use a different two scenarios. First, we assume the hematite is as coarse as the lunar regolith, like a 10, 20, or even bigger particle size. It gives us around like a 11 weight percent hematite. Now we also try to find very finer particle size for hematite. For example, maybe like a micron edge is coated on the surface. It also gives like a very good spectral fade, and also the abundance decreases a lot to like a few weight percent. This makes sense because it's all like coated on the surface, has a stronger spectral effects. So at this time, we from the optical data we have now, it's very hard to tell whether the hematite the particle size of a hematite is fine or coarse. It's hard to say, but it's not a nanophase. We also tried to fit the spectrum with a nanophase hematite. It can also not fit the spectrum well. So it should be micron size or bigger. Okay, so actually I am more excited about the implications than the detection itself. So this is one example I gave for so many implications for the presence of hematite. It can help to review the evolution of Earth atmosphere and also even the climate. But there's an assumption here. So the assumption is our hypothesis is correct. So the formation of hematite on the moon surface is true caused by the presence of oxygen delivered from the Earth to the moon. If that's the case, so we can sample hematite at a different age units. And so this is the left plot. I'm showing the oxygen density in the atmosphere versus the time. You can see there's a great oxygen event at around like 2.4 billion years ago. And I think there is still like a arrow bar here. And you can see as time goes by, we have more and more oxygen in the atmosphere. Well, like the moon itself is a natural laboratory, and particularly the subsurface is being preserved for, after its formation. If we can get the samples from the subsurface without like severe gardening effects, and at a different units of age, and if we can examine their oxygen isotope, and also if we can get the formation rate of hematite, that may help to understand the oxygen in Earth's atmosphere, and also may help to review some like variation of the atmosphere, for example, associated with the climate change. So this is oxygen 18. This is a daughter 18 isotope. Like in past 100 billion years, you can see the variation, and also you can see when the climate is cold, the delta 18 drops. So it's associated with the climate very well. And if we can get like samples back to like billions of years, like from the moon, and maybe you can draw like the curve like back to billions of years, and it can help us to review what happened like in the geologic history of the Earth. Okay, So in summary, this work shows us the first orbital detection of hematite on the moon, and we only see it at a high latitude, and we see more on the near side, and also more on east and equator facing slopes. The abundance is like from few weight percent up to like 10 weight percent. It really depends on the particle size, and which is a big unknown currently. The possible formation mechanism, we think this is associated with the water content at the high latitude, and also associated with the Earth's oxygen in the magnetic tail, and also boosted by the energy induced by the interplanetary dust impact. And as I mentioned, the oxygen isotope of hematite may help to reveal the evolution of Earth's atmosphere. And also, the hematite on the surface can be used as in situ resources. For example, you can use for iron. I mean, I'm not saying there's iron enrichment at this region, but just in different forms. So compared with the oxygen in pyroxene or like other mineral phases, maybe iron in oxides is easier to extract, and also it's rich in oxygen. Because hematite is opaque in UV, maybe we can use it for shooting the solar or cosmic ray irradiation. And also, the presence of hematite suggests that the polar region is chemically active. This is quite different with what we see near the low latitude, like near the equator, the Apollo samples what we see. So there could be more alterations, particularly at the S exposures in the dark region, like a permanent dark region. But currently, it's a knowledge gap. We don't have data yet. Okay, that's all I have. Thanks.
Awesome. Yeah, thanks, Shuai. And we have plenty of time for questions, which is great,
Oh my God,
because I'm
moving so
sure
fast.
people will have questions. So I see Tim had typed a question in the chat. So Tim, I don't know if you want to go ahead and unmute yourself, or I can read it out either way, but I'll wait a moment in case you want to unmute. Okay, I'm going to go ahead and read that out in case Tim's in
No,
a
no,
place
I'm
where.
here. I was just
Oh,
kneading bread
okay.
actually at the moment while listening. Yeah, the
Oh.
question was, so you, Shuai, you proposed a model with O2 plus from the Earth impinging on the lunar surface, but all of those iron atoms are currently hosted within a different crystal structure. So if this seems like a great prospect for an actual lab experiment to use a sample of an orthosite or basalt or something and irradiate it with your ion beam and see if you actually form something that is spectrally similar to actual hematite. Since we can, ramp the flux up way beyond reality, you ought to be able to do it within, a human lifetime at least.
Yeah, Tim, you are absolutely right. Yes, that's actually one of the project I'm thinking, and also one of the implications. Like, we can definitely do it, test it in lab, right? So it's like, we give the solar wind flux, UV, and also oxygen flux, and with the even like lunar analog, we can test whether we can see the whether they're hematite form. Yeah, you're absolutely right.
Okay, so I see Jeff Plesher has a question in the chat. Jeff, did you want to go ahead and unmute yourself to ask that? Wait a moment, otherwise I'll just read it out.
I was just sort of wondering how the hematite is forming. I mean, if you've got oxygen ions coming in to the shadowed area.
No, this is an illuminated region, not shadow.
Okay, so it's coming into the crater. You're just burying oxygen into the crystal or the glass or something, aren't you? I mean, how do you got to have some chemical reaction going on?
Yes.
To make the hematite.
Yes. So one of the possible scenario, in my mind, is it's helped by the interplanetary dust impact. So as we know, so in laboratory and also people see that when you bombard like a surface, a mineral in lab, there is like a plume form, right? So in the plume, people saw like iron oxides, not necessarily like a 3+, so maybe like 2+ ferrous iron. So if the impact happened like when the moon is in the magnetic tail, that means like you have oxygen available, and the impact can help to liberate like ferrous iron or other forms of iron in the eject plume, and the iron can meet with oxygen and even water, molecular water, right? So that has been also been demonstrated, like, so the molecular water can also be formed in impact. So you have oxygen, you have water, you have iron. So that's very easy to form iron oxide. After formation of like hematite or some other forms of iron oxide or other species, maybe it can be quenched very fast by the impact melt. Yeah, so that's just a speculation. I think I agree with what Tim just said. So it will be very interesting to do some lab experiment to see whether we can see this can happen.
Thanks.
Cool. All right. And I see Mahesh has a question.
Yeah, hi, can you hear me?
Yep.
Yes.
All right, great. It's a very thought-provoking paper. It caught my attention, so thanks, Parvati, for organizing this. I'm not putting my video on because I'm sitting in a car park in a grocery store in England while waiting for some grocery to be done. But I was just so intrigued by this presentation that I decided to sit in the car and listen in. I probably have too many questions, but sure, I read your paper earlier today when Parvati shared with us, and I wondered, I mean, in your paper, you go in a bit more detail than what you presented, I guess.
Yeah.
But you know, you expect this hematite to be present. I think you say somewhere there in the paper in the top few tenths of nanometer.
Possibly, but it's not necessarily. So, I mean, like, it really depends on like the formation environment. So there are two different formation environment I can think about. First is the implantation itself. So because the solar wind oxygen in the oxygen in the plasma in the magnetic is very high speed. It's a very high energetic. So it can be implanted on the surface. So if a planet on the surface meet with iron, it can form like a hematite. This is one possible scenario. The other one is what I just explained to Jesse. So like it can form during impact in the impact plume. I mean, this is a very fine scale, like maybe micro scale. So after formation, it can be quenched in impact melt.
Yeah, so my question was that, when you try to relate to the samples, clearly we don't have any samples from that 60 degrees latitude north or south, as we think we don't have. Maybe we have some meteorites, but surely not regolith. So we, certainly that will be one of the things that can be tested. So that's great. I wondered whether the other speculation, I mean, I might say it is a speculation because you yourself said that, is how oxygen isotopes could help. But the plot that you showed, for example, the terrestrial oxygen plot, I mean, they were all for oxygen delta 18 for a couple of per mil variation. I mean, what we know at the moment is that Earth and the Moon have almost indistinguishable oxygen isotope composition from all the samples that we have analyzed, right? So without knowing how much concentration you are expecting, really, we expect to see a difference in oxygen isotopes?
Yes. Okay, so there are two, actually more than two. I can send you papers afterwards. So there are a few papers, people examine Apollo samples. They found in Apollo samples, there are some of them showing poor in oxygen 16 isotope. So that's exactly the case on the upper atmosphere, right? So on the upper atmosphere, it's poor in oxygen 16. So that's also found in Apollo samples. This is 18 is just one example. Actually, what I want to show is oxygen 16. So there should be some variation in oxygen 16 because if all oxygen is from the upper atmosphere, and as we know, the Earth's upper atmosphere is poor in oxygen 16, and if there's some changes in the Earth atmosphere, that should be also changes in the Apollo sample, in the lunar samples, in the fossils.
Yeah, I guess you are referring to some of the iron profiles that were done long time ago in these individual soil grains. Where
not a very long time. I think it's like around
1980s.
No. 2009-ish or 10-ish. I can send you papers.
Oh, that's great. Okay, all right.
Yeah. There are multiple papers doing this work.
Okay, that's great. Yeah, thank you very much. Yeah, I will follow up with a few more questions later on. I won't bore others with that, with that. But it's a very very interesting paper. Thank you.
Thank you.
All right. What other questions do we have for Shuai? Oh, I see Ariel has her hand up. So Ariel, go ahead.
Thanks. Hey, Shuai.
Hey, Ariel.
I was curious if you've thought about the time scales for hematite formation and what that would mean.
You mean like how long it would take to form the hematite? What do we see?
Yeah, and if it's forming from water there, how long would the water have had to be there already?
Oh, well, okay. So if we are thinking about like the PSRs, the ice, I think it can be very fast. So I mean, like we know it's airless, and it's the impact happens all the time. So when the impact happens, you have energy, and you have water, you have rock. So that's essentially what we see. Like in lab, you can do you heat up samples with the water, the increased alteration can happen, right? So I feel like it can be very fast. So that's why that makes me speculate in the PSRs. I think we should be able to see some aqueous alteration products.
Thanks.
Did I answer your question?
Yeah, thank you.
All right, what else? Okay, while people are thinking of more questions, I'll ask one.
Yeah.
And like Mahesh, I have a whole bunch of questions, but so well, do you see any correlation of the hematite with I mean, is there a difference between focusing on the water component, if that's one of the ingredients you need, do you see any difference between the North and South Pole, or between the paleopole locations, or any correlation with the M cubed ice exposures? I'm sure you looked at a few of these things, but is there anything there?
Yes, that's a really good question. I think one of them can be answered by here. So like, I'm not sure this is a coincidence or this is true. So do you see this?
Yeah.
Yeah, so this roughly sounds like, there are more on us. This is a northern polar region. So it seems like there's some rough correlation with the abundance of water. But this is really hard to say whether this is coincidence or really due to water, because as I said, the possible role of water in the formation is not like static water. What I mean is like the water formed during the impact. I mean, like possibly if you have like a hydroxyl or whatever species of water, OH or H2O on the surface, but if you have more on the background when the impact happens, you can have more chance to form, right? To form like water. So in theory, there should be some like a correlation, but I cannot answer this directly. And also the other one is whether the polar wonder, the paleopole. I was thinking that question actually for a while, but after a few, like it's maybe hard to to solve, because even though, based on our theory, hypothesis, even though the hematite can be formed at a lower latitude, I mean, like, as you can thinking when the pole wandering, but the hematite at a lower latitude cannot be preserved, because the solar wind flux is so strong. So anything you form, it can be destroyed. So even though there could be some, like a distribution pattern, but after the moon was on its current axis, I feel like the solar wind flux can trim all them off to the distribution pattern what we see now.
Mm-hmm. Yeah, that's really interesting, and you kind of raised another thing I was wondering, which was about the loss processes, and so this is kind of related to Ariel's question about timescales as well. But so so the hypothesis is that if you have water, a relatively oxidizing environment, and energy from IDPs, you can generate hematite. So, and now I forgot what the question was, but I remembered it. But yeah, so the hypothesis that you have these three ingredients, you can create hematite. But then, are there destructive processes as well? So once it forms, does it just stay and get garnered in, or can it actually turn into something else?
Yeah, I think So there's a destruction process all the time by solar wind implantation. So if it's formed on the coating surface, it can be destructed like maybe very fast by solar wind implantation, because hydrogen it's lighter than oxygen, right? So the implantation of oxygen could be shallower than hydrogen. So like on the pathway to form hematite, like in the rim of the grain. So the hydrogen maybe can just travel way deeper than oxygen. It can destroy anything. Like, it can bond with the oxygen and go away or stay to reduce it. But if the hematite formed, like quenched in like a glasses on the surface, so that means it can be deeper, can be well preserved. So that may stay much longer. So that's why I'm thinking like even though we grab samples from the surface, and if some of the hematite formed like quenched in agglutinates a very long time ago, that still can give you some like time scale, like a from old to young. And also another way to do is to dig, right? So it's like, as we know, like as it goes to deeper, maybe meter or even deeper, that can be less affected by gardening and overturn. So you may have like a better records. Yeah.
Mm-hmm.
Yeah.
Cool. And I see Mahesh had a question in chat. So could you comment on the possible mineralogy at high latitude? So for instance, Mahesh asks, are there many iron-bearing minerals expected versus pure anorthosite?
Yeah, that's actually not my work. So that's Paul Lucy's graduate students, Mariam Lemney. So her PhD thesis is about this, the whole polar region. It turns out, I'm not sure she's on. So the major minerals in the polar region is like plagioclase and andesite. So there are not many like pyroxene or olivine from the orbit that we see, even though there's some like craters, fresh craters showing strong pyroxene absorptions. Yeah, so mostly majority should be andesitic. Yeah,
Cool.
but there's still iron in, well, like there's iron in plagioclase, right? So even though it's like it's not so high as pyroxene or olivine, but it's still there are iron available.
So sorry, sure. If I can just come in, Parvati, is that okay?
Yeah, go ahead. Go
so
ahead.
yeah, so if we want to get 10 weight % hematite from an orthosite, I don't know unless I'm missing something. I find that very, very hard.
Yes, right. So that's and also that's the high end of our value, right? So
even 4% hematite, I think, is very high for an orthosite. I can tell you that.
Okay. Well, that's
Yeah,
good to
I'm a
know.
sample person, so I know a little bit about samples, and so I can say that that seems high because you are almost converting all the iron and some more into hematite. So I think we got to think about that, and it will be interesting to see if you see any difference or correlation at some level to the mineralogy expected in one region versus the other. You know, if there is more mafic minerals present somewhere, maybe if you see more of that hematite signature.
Oh, but yeah, that's definitely a good suggestion. Yeah, I will talk to Mariam, like get her, to try to get her like a mineral mapping. Or I think she did some iron mapping too. So maybe I can do a comparison, see whether I see more hematite at like a high iron content
Yeah,
region.
yeah. And while I have your attention, I will just read out the other comment that I posted to save Parvati at some time. But, when we are discussing about the possibility of finding hematite in those water-rich polar latitudes, and if
Yeah,
we consider kind of presence of water to be the key factor in the formation of these hematites, then with the same argument, one would not expect those hematites to form in equatorial regions, no matter what, because as far as we know, there is no water ice available in the equatorial region.
right. Yeah, that's the way I argued in the paper. Yes.
Okay, great. Thank you. Thank you. We
Yes.
can't wait to get some polar regolith samples in our hand to see what it
Oh,
is.
yeah, exactly. Yes, I think we will. It will if we can get samples from the polar. It will definitely surprise us for sure. Yeah.
And Junichi has a comment in the chat. So Junichi says almost the same question, but even at the higher latitudes, there are Mare deposits where the things should be more iron rich. And so do you find hematite in
Yeah,
such
kind of
regions?
interesting, like a southern polar region, right? So that's South Poican. So that's a lot of Mare region, but that's on the far side. So that's side. I mean, like you can see. Oh, but I can go back to the map. Yeah, so here, I mean, this is a Schrodinger, right? So this is South Poican. So a lot of my region, but because the far side I don't see many exposures. And on the near side of the crater walls, actually, I examined the spectra of the crater walls. It looks like another acidic because it looks featureless. There's no strong absorption, like showing like either pyroxene or olivine. And also this, I mean, like this is a impact on the anorthositic crust, right? So based on multiple like observations, I think the majority of the exposures are associated with the like anorthositic crust, not the like a pyroxene or Mare-rich region. Yeah, but I think it's a good suggestion to compare like the exposure, the band depth with the iron content and see whether there's some correlation. I think that's a good suggestion. I would definitely do that.
Okay, so we might have time for more questions. So keep thinking, everybody. But also, I know that Ariel Moulet wanted to make an announcement about some Sophia lunar observations. So, Ariel, since we have you back, did you want to go ahead and talk about Sophia?
Oh, yeah, sure. Can you hear me?
Yeah, loud and clear.
Yeah, so my name is Ariel Moulet. I work at the Sophia telescope, but I'm a planetary scientist, not a lunar one. I work mostly with asteroids and atmospheres. And when I contacted Parvati, I wanted to let like a month ago, I wanted to let her know of this upcoming paper in Nature Astronomy. But in the meantime, it came out and it actually made some waves. So you may have heard about it already. Molecular water detection on a high latitude crater in the moon. So using this infrared telescope Sophia, the 6 micron feature was detected, and that one is really telling of water, of molecular water. So before that, actually 3 micron feature had been detected with MQ, but that's the one that is harder to disentangle, where it's a hydroxyl or water. So yeah, we were really happy about this result. And I know the team has more plans to explore that 6 micron feature in other places on the moon. It's quite a challenge for our telescope because the moon is bright, so it pretty much blinds the receivers for a while. But I think it's a problem with moon observation oftentimes, I'm afraid. And Casey Honeyball, the main author, she will have a poster at AGU in a Sophia session, and I'll try to make a Q&A happen. I mean, AGU is a bit complicated this year. They're still figuring out which events happen and which do not. So, but you know, I may forward to this list if there's a Q&A happening.
Yeah, definitely. Yeah, please do. I mean, yeah, that was super exciting.
Okay, so you heard about it.
Yeah. In fact, so Ariel, this was before you joined the listserv, but actually, a few months ago, I think maybe this was last November, but we, while Casey was still writing this up, we actually had Casey present on some of this.
Great.
I think this was in November. So yes, it was really exciting to see the paper come out. And yeah, I'm really looking forward, and I'm sure all of us are really looking forward to the continued observations from that as well. I mean, it's you know, it's a really cool result, you know, and the fact that it's using Sophia, you know, and it's a ground-based observation. That's exciting as well.
Yeah. Okay. Well, I hadn't heard that Casey had given a talk already, but I'm glad she had, and yeah.
Yeah, this was, at that time she was, you know, I think she talked to us maybe a few weeks before she was due to submit her dissertation.
Yeah, got it.
So yeah, but that was exciting. Okay. But yeah, thanks for sharing that.
No problem. I'll send the link to the paper in the chat.
Mm-hmm. Yeah, that'd be great.
That's it.
All right. Do we have, let's see, we have time for maybe one quick question, and I see Mahesh has one for maybe both of you, but can Clavius crater be searched or mapped for hematite?
No, that's 50-ish latitude, so the latitude is low, and also that's nearby a Tycho crater. So part of the region actually was covered by the Tycho ejecta. This is it's kind of interesting because they did a very good shot, because the Sophia observation just hit on the region like it's not affected by the ejecta. So sounds like that's the older region has been preserved, and nearby is a dry region. So yeah, that's really interesting. Yeah.
All right, awesome. So we are just coming up on 3, according to my clock. So yeah, I think we will call it a day, and I will encourage people to reach out to Shuai and Ariel and then Casey as well, if folks have questions. And all right, so thanks Ariel for that, for sharing the Sophia announcement with us, and thanks Shuai for a great presentation. It's this really interesting work, really interesting hypothesis to test. So yeah, and thanks everyone for calling in. So we probably won't meet in December, but I will, because of AGU, but I will send out an email, and we will, I'm sure we'll have lots of more exciting volatile science to talk about in 2021. But yeah, so since this is our last call for November, I hope everyone has a very good Thanksgiving, and as we get into the holidays, I hope you all get to take some well-deserved rest and spend time with your families. But yeah, thanks again, Shuai, and thanks everyone for dialing in, and we will call it a day, and I will send out the recording shortly. Thanks, everyone.
Thank you, everyone. Bye.